Welcome to Chapter 8, Continued. I'm going to look in more detail at the function in the neuromuscular junction, how the ions move, and how that action potential is transferred to a contraction at the sarcomere level. I'm using McGraw-Hill animations, which is a different company than your textbook, but they're beautiful animations, and very informative. So here we go. When you look at the axon, so here's the axon, which is the end of the nerve. You have your vesicles, and inside your vesicles are your neurotransmitters. This is the calcium channel, and these are sodium channels. So I'll play a little bit, and then we'll go through it in detail.
An action potential arrives at the presynaptic terminal, causing voltage-gated calcium ion channels to open, increasing the calcium ion permeability of the presynaptic terminal cell membrane. Calcium ions enter the presynaptic terminal and cause vesicles to release their neurotransmitter acetylcholine from the synaptic vesicles into the presynaptic cleft. Diffusion of acetylcholine across the synaptic cleft and binding of acetylcholine to acetylcholine receptors on the postsynaptic muscle fiber membrane causes an increase in the permeability of ligand-gated sodium ion channels.
Okay, let's review that from the beginning. We always talk about calcium being very important for a muscle, and it comes right down to the propagation in the nerve. So the action potential comes down, it opens calcium channels. These calcium channels will then trigger the vesicles to release their neurotransmitters. Here we're talking about acetylcholine, but there can be other neurotransmitters depending on the action we're looking at. The neurotransmitters will then go into the synaptic cleft, and if there's enough of them, they will bind onto these gates, and these gates are sodium channels. If there is enough acetylcholine bound at them, the sodium will then be able to diffuse through the channel, and if enough sodium goes through, it will cause an action potential, which we'll talk a little bit more when we talk about nerves. There are ways for this, and this will keep going until this neurotransmitter is removed.
The postsynaptic membrane. Once threshold has been reached, a postsynaptic action potential is generated and is propagated over the muscle cell membrane. Acetylcholine is rapidly broken down to acetic acid and choline in the synaptic cleft by the enzyme acetylcholine esterase. The choline is reabsorbed by the presynaptic terminal and combined with acetic acid to form more acetylcholine, which enters the synaptic vesicles.
Okay, so the reaction will occur, or the potential of the reaction will occur, as long as this acetylcholine is on the sodium channels. If the acetylcholine stays bound, the sodium can go in. Now, quite often there are conditions and one example is spider toxin. Spider toxin will cause this muscle to contract by interfering with this breakdown of acetylcholine. The acetylcholine can be removed. Usually it's broken down by an enzyme and reabsorbed. If you do anything to interfere with that enzyme, you will interfere with the reaction or the transfer of the action potential from the nerve to the muscle. So just a quick look at it. You have the action potential come down, calcium opens, vesicles move, neurotransmitters released, neurotransmitter binds to the channels, and if there's enough sodium, it will trigger an action potential. So that's what's happening at the neuromuscular junction. Okay, I'm continuing on with the McGraw-Hill animation. Now, we've got the action potential coming to the contracting unit, which is a sarcolemma. The sarcolemma is another word for the outside. Then you've got this sarcomere, which is this line to this line. when we look at this, let's look at the players. You've got a thin actin protein, and you have your thick myosin, and the thicker myosin has the heads. You also have what's called a sarcolemma. No, this is a sarcomere. This is where the calcium is stored. And then there's what are called T-tubules. The T-tubules is just a way to expand the surface area, allowing the calcium to go in. So let's play and then we'll review.
Action potential introduced at the neuromuscular junction is propagated along the sarcolemma of the skeletal muscle. At the T-tubule, the action potential is propagated on the T-tubule membrane into the interior of the muscle cell near the ends of the sarcoplasmic reticulum. The depolarization of the T-tubule membrane causes nearby voltage-gated calcium ion channels on the sarcoplasmic reticulum to open, resulting in an increase in the permeability of the sarcoplasmic reticulum to calcium ions.
Okay, a lot of detail there. You don't really need to know that much. Just want you to realize the action potential comes. It travels along the T-tubule and will cause the release of stored calcium. So again, calcium is important.
In the permeability of the sarcoplasmic reticulum to calcium ions. Calcium ions then diffuse from the sarcoplasmic reticulum into the sarcoplasm. Long filamentous tropomyosin proteins lie on two sides of the actin myofilament, covering up the sites where myosin can bind to the actin myofilament. Globular troponin proteins are attached to the tropomyosin.
Okay, let's look at the two proteins. We talked about actin being thin and myosin being the fuzzy one with the heads. Actin's actually a complex. On the actin, you have sites where the myosin head can bind, but when you want your muscle to relax, those binding sites are full, and they're full because they're covered with tropomyosin. Now, in order to get onto the tropomyosin is another protein called troponin. So troponin, tropomyosin, binding sites, myosin microfilaments.
When calcium ions bind to troponin, this causes troponin to change conformation and move the tropomyosin. When the tropomyosin moves, this uncovers the myosin binding sites on the actin, allowing myosin heads to bind and form cross bridges. The cross bridges play a role in muscle contraction.
Okay, so you've got calcium comes, binds to troponin, causes troponin to change shapes, pulls the tropomyosin off of the binding sites, and the myosin heads can now bind to these binding sites. Okay, now let's get an idea of what's going on in the sarcomere before we look too much at the head. What we have is our thick actin, and on the actin is the troponin and the tropomyosin, and here we have the thick myosin. Don't pay attention to the A bands and H bands, and just Z line is the only thing you need to know here.
In a relaxed muscle, actin and myosin myofilaments lie side by side, and the H zones and I band are at maximum width. During contraction, the actin and myosin myofilaments interact. The actins are pulled toward the center of each myosin myofilament. As a result, the sarcomeres shorten. In the fully contracted muscle, the ends of the actin myofilaments overlap. The H zones disappear, and the I band becomes very narrow.
Okay, this process is called the sliding filament process. Nothing actually changes shape. You have your myosin and your actin, and they stay the same length, but they slide past each other. To me, it kind of looks like a bunch of little rowers. But the myosin head will grab onto the actin and pull these Z lines closer. So that's why it's called the sliding filament theory. Now, let's look at a little more detail on the myosin heads. When it comes to myosin and actin, ATP is also needed for the reaction. That's why this process needs a lot of energy. So a quick summary to give you what's going on.
During contraction of a muscle, calcium ions bind to troponin. This moves tropomyosin out of the way and uncovers binding sites for myosin on the actin myofilaments. ADP and phosphate are attached to the myosin head from the previous cycle of movement.
Okay. When it comes to ADP, hopefully remember that ATP, when it breaks down, it gives off ADP and phosphorus. So what happens is the ATP has already given its energy to this myosin head to activate it.
The myosin heads attach to the exposed binding sites on the actin myofilaments to form cross bridges, and the phosphate is released. Energy stored in the head of the myosin myofilament is used to move the head. This causes the actin myofilament to slide past the myosin myofilament. The ADP is released from the myosin head as it moves.
Okay, so let's look at that again. The head attaches. Because of the energy in that head, the head will have its power stroke and bend. Then we haven't talked about that yet.
Myosin head as it moves. The bond between actin and the myosin head is broken when an ATP molecule binds to the myosin head. The ATP is broken down to ADP and phosphate, releasing energy, which is stored in the myosin head and will be used later for movement. The head of the myosin molecule returns to its upright position and is ready to bind to actin again.
Okay, so let's look at that. There's a binding of the myosin head, the head bends, and then along comes ATP. ATP is that cellular energy which is needed to break the cross bridge and reactivate that head, and it goes back to its power stroke.
To actin again. If calcium ions are still present, the entire sequence is repeated.
And this will keep repeating until until the calcium has been removed and put back into the sarcoplasmic reticulum. Then when the calcium is removed, the troponin will change shape and the tropomyosin will cover the binding heads again. So this is important to realize that ATP is needed. When someone dies, their body gets stiff. And the reason why the body gets stiff is the muscles stay in this contracted form. So rigor mortis or stiffness sets in. Okay? Pretty good summary. Hopefully that helps. You need to know this detail.